are the two people that I have to dedicate this presentation to, because these are my parents, and they are the two most inspiring people that I've ever known. Unfortunately, they couldn't be here today, but I understand the cameras are rolling, and so hopefully they'll get to see this at some point. The other group that I definitely need to dedicate this talk to is all of my amazing students that I've had for almost 10 years now at Cal State Fullerton. There's way too many of them for me to name each one, but I've had such extraordinary good fortune to be able to work with such a wonderful group of math students here at Cal State Fullerton. So I want to welcome you to our campus. This is a place that is a really large institution. We have a huge number of students and faculty, math majors, and bachelor's degrees awarded every year. And it might be easy to think that you can lose track of people very easily in such a large place. But I love this place with all of my heart. And one of the reasons that I love it is that I've been able to try to find ways to make this large university smaller for the students that I've had a chance to interact with. And the university has facilitated that for me as well. So welcome to Cal State Fullerton. It's great to have you here. How is it that we can try as faculty members to create a student experience that is intimate and personal despite being at a large institution? And what I'm about to list here are things that will apply at any institution. I know some of you are not here from a particularly large institution, but some of the things that we're going to talk about I think are very relevant to us as teachers and mentors, and so it's worth mentioning some of these things. So, for example, I think it's really important that we put a premium on developing support communities for students. The other thing I should mention before I go any further is that I know that some of you out there are not teachers, you're actually students. But all of us at some point in our life are going to be both teachers and students. And so even if you're a student and I sound like I'm talking to a faculty member, this could be stuff that will be relevant for you someday. Probably will be relevant for you someday. So what sort of support communities am I talking about? So things like getting involved with the math club at your institution, getting involved in problem-solving activities such as the Putnam exam. That's something that's become of great interest to us here at Cal State Fullerton. And doing the kinds of things we're doing today. Traveling to conferences, presenting our class projects, and other activities. These are the sorts of things that I think make the students feel like they're getting a much more intimate and personal experience, regardless of the size of the institution that we are at. Another thing that I think is really important that a lot of people don't think about that often, as instructors, I think it's really important that we try to teach at all levels of the curriculum. You know, the students aren't with us all that long. They're only here for 3 or 4 years usually by the time we know them. And if we take the opportunity to teach courses at the beginning of their curriculum, we actually have a chance to really get to know them well over the course of time. So I encourage you to embrace those opportunities to teach courses that are freshman level introductory calculus classes, because you really get to meet people and keep in touch with them for a much longer period of time that way. And for all of you country music fans out there, of which no one could be greater than me on that score, there is a song on the radio that you probably have been hearing lately that I really love the message to. It's called Time is Love. If you want to see what people love, look at how they spend their time. That's exactly what I try to show my students, that by putting a lot of time into them, you're really demonstrating your love for them. Now, we only have a certain amount of time in the day. It can be very difficult to do this. So this isn't necessarily for everybody, but I tend to like to take a lot of things from my personal life and combine them with activities with students. So I like to try and stay in shape. And one way to do that is to get out and exercise. So why not play a game of basketball with the math club or play some racquetball? I used to play racquetball. Kind of gave that up. Or we all have to eat. So since I can't cook, or at least you don't want to hear stories about that, I think it's better if I just go out to eat. And there are often armfuls of students around that want to do the exact same thing. In fact, I've on occasion held office hours off campus, so it's not really an office. I got a little tired of the food at the same restaurant after about 4 years, but it got people to come out and see the human side of their instructor And, you know, it's not for everybody, not what everybody's necessarily going to want to do, but it's something that's helped me to find time to give to my students. So, how do I cope with all of these copious amounts of activities that I try to keep engaged in? You know, it's tough to really give and give and give and give and give. But there is a coping mechanism that I like to take advantage of. I kind of have a double life, or I have no life. I'm not sure which. But I'm going to think positively and think that I have a double life. And so for 9 months out of the year, I am Professor Scott Annin, as you can see right here. But I do something very different in the summer to sort of disengage myself for a little while and refresh my batteries and recharge. And it's something that actually I think helps me to stay afloat, if you will, during these other 9 months of the year, which is I go out and I spend a lot of time hiking. And I'd like to tell you a little bit about my hiking experiences. I do this out in Colorado at a YMCA facility. But there's just one problem. I have seen a lot of things out there in Colorado. I've seen a lot of things. I have never seen anybody go on a hike in a suit. So, we need to fix that. Danny and Carol, could you guys come down here for a minute? Excuse me. Could you just take everything out of that and set it on that table? I've got to get these poles fixed up. Oh, never mind. I'm not going to use the poles. It's way too warm in here anyway. Now I guess I'll put this here. No, you can't hike with a suit and tie. It just doesn't work. So, you live a double life, you have to have 2 different wardrobes. Here we go. What do we got? Anything? Anybody hungry? Oh, thank you very much. Let's see. Sunglasses. Where's my cat? Here we go. Oh, actually, I might like this one better. Cal State Fullerton. Let's try this. Okay. Oh, never mind. All right. You guys don't mind if I change, do you? I promise this will be family friendly. There we go. This is looking more like it. Now, I'd get in trouble for wearing this shirt too. They make us wear this crazy gear. I should try putting things on in the right order. I didn't practice this. There we go. There, that's much better, right? Except I can't see you now. May I take off the glasses? Okay. I'll take off the hat too. So anyway, now I'm a little more suited to talk about what I want to do next, which is tell you a little bit about what I do in the summer out in Colorado. So I'm a hike master. This is not a word you'll find in the dictionary, but it's a very unique, one-of-a-kind center in Colorado, up near Rocky Mountain National Park. There is a YMCA center up there, and this is how I refresh and recharge my batteries during the summer months. Lots of people come out and visit and take vacations and just hang out and go hiking, which is what I like to do. There's kind of a picture of it from above. There's hundreds and hundreds of acres there on the main base camp. And it's a lot of things that we get to do out there. So what exactly do we do? Well, there are a lot of hike masters that work every summer out there, and they come in all shapes and sizes, young folks, old folks, people who are involved in math, and people who do all kinds of other things too. And in fact, there are quite a few math teachers and math students that have come through the hike master ranks in the summers that I've been working there. So what is involved is I lead people on hikes in and around Rocky Mountain National Park, which is about an hour and a half away from Denver. And this is probably the picture you have in your mind of what a hike master would do. Hike master is going to talk to the people that he's leading about what they're seeing on the trail out in nature. But actually, it's a lot more than that. This is not just a standard little hiking program where we just stay on the trail all the time. We like to hike for 6 hours to get to the top of a glacier so we can sled down. You have to get up at about 3 o'clock in the morning to do these kinds of things. But it's worth it. It's worth it. If you tried it once, you'd love it. Okay. I love this picture. This picture was taken by somebody I don't know, who is on top of the mountain that I'm currently, do you see those little dots there? I'm the guy right there in the front of the line leading these people across that snow, and in about 3 hours we're going to meet halfway to the top of that mountain. So it just gives you some perspective on the kind of stuff there is to do out there. Sometimes you're just forging your way through boulders and slabs of rock. It's a rugged country. They do not call it the Rocky Mountains for nothing. Okay. So there's a lot of training that is involved in this, as you can kind of imagine. You know, not quite doing a PhD, but sometimes feels like it. So if anybody has a heart attack in the next 45 minutes, I'll try to help you, but please don't do that. Wilderness First Aid training course consists of all kinds of different components here. Some geology, some maps and compasses, how to walk on snow, etc., that we teach. And I actually teach a class, one of the classes that we have out there, which is on leadership and safety. So leadership and safety involves a lot of components, one of which is, you know, the terrain and the weather. Here's a bad situation right here, clouds and storms coming in. Here's snow running right next to a river. That's very dangerous, actually. You don't realize there's water running underneath there. Here's a snowstorm. We turned around that day. And here we're sledding down hundreds of feet towards this lake, but you got to be able to stop before you go into the lake. So all that takes training. So there's the elements that you have to deal with. But there's more than that. There are also the people that come out and go hiking with you. So I have some pictures. These are not just average people. These are my students and colleagues and friends from Southern California that have come out and visited me. So these 4 guys came out, 4 of my students, and they will tell you, or they would tell you if they were here, how hard this stuff is that we do, because after day 1, these 2 guys threw in the towel. I actually tried to take them on the easiest possible thing I could think of, but it wasn't quite easy enough, I guess. So by the second day, all I had left were these 2 guys, but they had a real good time when it started raining, putting on this high-tech rain. Here's a couple other folks. Some of you might know. I think he's here somewhere. Burrow Klassen, one of my colleagues in the department. Yeah, he's there. He's up there. He and his wife, Jane, came out and visited me 4 years ago in the summertime. And these guys did the right thing, which is when they saw this, I don't know if you can see that. That is a duck sitting there. You know what people like to do? They like to feed the wildlife. They like to just give them all kinds of, you're not supposed to do that though. So these guys were restraining themselves. Jane took a picture of the ducks as they come out of the lake to try to get food from these 2 guys. But you know, when we all go home in the winter, there's nobody there to feed them anymore. They've got to be able to find food on their own. So we kind of have to lay down the rules too sometimes with these folks. Here's another one of my colleagues who's here today. Marika Klassen teaches at Fullerton College. She came out and visited me a couple of summers ago, and she also did the right thing. She told me before we started hiking that she's afraid of heights. And so I was able to pick hikes that she wouldn't get scared on. Unlike this guy, who didn't bother to tell me that. It's another one of my students. And we're climbing to the top of that thing, and this is like 18 miles that we're going to travel to get to the top of that thing. We got all the way up there, and the wind was blowing and howling, and that is a very, very pointed summit at the top. And he got kind of frightened up there. And I didn't know until that time that he was a little bit afraid of heights. So this is what the coming down part of the hike looked like. Here he is, kind of crawling down the mountain. And that may look like he's only got about 10 feet to go. No. He's got to go all the way down to that lake. So this took more than a few hours. But, you know, if you just tell the hike master before you start that you're afraid of heights, I won't take you there. Okay. So the people, you've got to manage the people a little bit too. The elements and the people. In a lot of ways, being a hike master is not all that different from being a teacher. And I'd like to share with you a couple of the PowerPoint slides that I put in my summer hike master leadership class. Some of the outdoor skills that a leader has. I kind of break them down into 2 parts. Hard-edged skills and soft-edged skills. And the hard-edged skills are the things that people are always thinking about. You know, did the hike master plan well for the hike? Do they have the technical knowledge? Do they know how to hike across boulders correctly? Can they make tough decisions like, sorry guys, we've got to turn around today? Or deal with conflict and crisis. These things happen miles and miles from a phone, right? And this can be this is a very serious thing, and hike masters have to be well prepared to deal with those things. However, equally important are what I would call soft-edged skills that involve sort of developing the trust of the people you're hiking with, communicating with sensitivity, showing them that you care about them, and inspiring them in some way to really be excited about what they're discovering and seeing out in nature. So if you think about it, almost everything that's on that slide would also apply equally well to a teacher. At any level of the curriculum, I think a teacher needs to have both kinds of skills. And we spend a lot of time evaluating people on this left side. You know, do they plan well? Do they know their stuff? Do they maintain their high standards? Et cetera, et cetera, et cetera. But something that's a lot harder to capture and a lot harder to measure are the things on the right-hand side. Communicating with sensitivity, inspiring your group, being excited about what you're doing. And I think we all would like to think that we're really good at this sort of thing. But I think it takes a conscious effort to be good at this over time to the point that your students really take notice of it. And I think almost everybody that I've ever met does a really good job on these soft-edge skills. But I think they deserve a little bit more attention. When you have the soft-edge skills, you no longer look like the obstacle. You no longer look like the person that's holding somebody's grade hostage. Rather, you look like the person who is leading these people on their journey towards a higher perspective and a greater understanding of whatever it is that they're trying to do. And it might be really, really hard. This is really, really hard. Okay? But if you've developed that trust and that sensitivity towards the people you're hiking with, they will follow you, or at least try to. And that means a lot when you're out there in the mountains. Okay. So when you have the soft edge skills, sometimes it gets a little bit easier outside of the classroom as well. I want to show you an example of this. Sometimes a student-centered project will just show up on your doorstep. At least it did for me back in 2006. I don't think Jairo is here today, but Jairo Aguay was somebody who worked with me a few years ago on a project. He came by my office at about 10 o'clock at night, and I have no idea why he came to me, because he wanted to tell me something about the Fibonacci numbers, which I don't know anything about. So he wrote down this list of Fibonacci numbers, and I said, okay, Jairo, that's great. So I said, what do you want to tell me about these? He said, you know what, I started arranging these numbers in different ways. So here you can see that what he did is he took the Fibonacci numbers and arranged them into two columns. And he noticed that there's a relationship between the odd indexed Fibonacci numbers and the even indexed Fibonacci numbers, in that they are all 3 times the number directly above them in that column, minus the number that is 2 above them in that same column. Okay, so he started making a table. The coefficient of the number directly above the current number, and was there a sign change on the number that is 2 above that number in the list. So there's a plus here, minus here, 1 and 3. He said, let's try it with 3 columns. And he found that the coefficient here is 4, and switched back to plus again. Okay, so he just, I don't know where he came up with it. I did not ask him to do this. He just was playing around one day and came up with this idea. 4 columns, 5 columns, any number of columns. There's a coefficient of the number directly above the current number in your list, and a sign change that alternates positive, negative, positive, negative. So what he actually had done, you guys recognize these numbers? Those are actually numbers that are following the same Fibonacci relation, right? Except the initial conditions are different. Different initial conditions, but the same recurrence relation defines the sequence. It's called the sequence of Lucas numbers. So they're the same recurrence relation that you're used to seeing for the Fibonacci numbers. And here they are, laid out. And they were showing up as the coefficients of the number that was directly above the current number in the current column. And so this is actually making the formula more precise. The nth Fibonacci number can be described by this formula right here. And that was eventually what we figured out, and we collectively kind of worked out a proof of this. But in some ways, I don't even care about that part so much. I mean, there are, of course, hundreds of recurrence relations involving Fibonacci numbers. And you go look them all up, and yes, you know, this one, I couldn't find it, so I assume it's fairly new. I didn't know. But that isn't even really the point. The point for me was what this did for that student, which was 2 years ago at this very MAA meeting, which was held at Harvey Mudd College, Hiro was proudly talking about the work that he had discovered in the form of that poster. And he was pretty excited about it. And so this is like one of those moments that I probably won't ever forget, because a student sort of who, I don't think, you know, he was not particularly well trained to be doing research in math or discovering it, but he went ahead and did it and took himself to a place that he probably didn't even think he could go. Sometimes you actually have to generate the excitement yourself for your students. It doesn't always just come into your lap. So sometimes you have to take the initiative to ask a good question. I want to talk just for a minute about what kinds of questions, or what makes a good question in undergraduate mathematics. And a lot of you know these things already, but I just want to re-emphasize some of them again and show you an example or two. You know, it's really great if you can come up with questions that are easy to formulate and which don't require the students to spend an enormous amount of time. Remember, they're not going to be with you that long. If you want these experiences to really benefit the students as they get ready to prepare for graduate school or whatever else they're going to do, you know, you got to start early. You've got to be able to make progress quickly enough. If they're just finishing this up, you know, weeks before they graduate, it can be a little bit difficult to take advantage of it fully. So I like to find things that can come quickly to the students, and then have quick avenues of exploration available, special cases that they can study easily, and lots of different examples that they can play with, maybe on a computer or elsewhere. These are the kind of ingredients that I think make a good question. Now that, of course, limits them somewhat on what they can work on, but if you're willing to work on those projects with your students, you can get into them pretty quickly. We all have a short attention span, at least I do. I don't want to have to work and work and work to get to the point of being able to work on a problem with a student. So let me just give you an example of what I think is a good question. How many stars have 1,000 points? Now I'll tell you, first thing I have to say, this is not my question. I did not come up with this, but I like it a lot because this question has lots of avenues of exploration that are readily available. Everybody knows what a star is. And you can start with 5 points and draw an example of a star. Anybody can do that. And well, then you can ask the students, could you draw a star with 6 points? Well, we have to have the definition of a star, which in the context of this problem takes like a whole page to explain. So I'm going to trust you that I can get away without defining a star fully with its like 6 different conditions. I think you know what a star is. One thing about a star is that the lines have to cross themselves and that the figure has to be completely connected, right, to be a star. If you think about those conditions, you'll realize you cannot have a star with 6 points. Well, I should say, also the segments all have to be the same way. You cannot have a star with 6 points. But that might not be obvious to a student, okay? And you can talk about stars with 7 points, or 8 points, or 9 points, and 10 points. Anybody can draw these pictures. I say undergraduate mathematics here, this is something that somebody at a much younger level could pursue. And in fact, this question came out of the American Mathematics Competition series that's sponsored by the MAA about 8 years ago, I think. And it was written by somebody in the audience. Stephen Davis is here today. He wrote that question, and the answer, 199, is, I'll leave it to you to work it out, okay? It becomes a very interesting number theory problem. It essentially, when you're looking at the stars, you're just having to ask yourself, well, how many points do you have to skip in going from one point to the next one as you draw these line segments? And certain numbers are allowed, and other certain numbers are not allowed. But it's not even really the answer that I think is all that interesting. Rather, it's the process of coming up with the answer that is really the most exciting part and where the real joy is to be found. And I think we would all agree about that with mathematics, right? The joy is in the process of discovery. not so much in what the final answer itself was. That's important to keep in mind. The joy is in the journey, it's not in the destination. Because you're not always going to get all the way to the destination. In fact, almost the definition of a good problem is one that always leaves more room to explore and go further. You're not always going to be able to do that. You're not always going to be able to reach a finale, if you will. So that's even true in the hiking world. Okay. So a couple of years ago, I had a couple other students who came out and visited me in the mountains. This is Andy and George. And we were going to hike to the top of that thing right there. From this lake. Now, we've already hiked about 5 miles when we got to this point here, so we're already a little bit tired. We're going to hike to the top of that thing right there, and then we're all real happy we're about to go up there. Obviously, we don't go up this side. We don't use ropes, in case you're wondering. We don't do anything that's that technical. Ice axes and ropes and all the special gear, we leave that stuff home. So to really get to the top of that thing, what you have to do is hike through these trees and then go up the backside. The only thing that you can't see from the picture is there's a whole bunch of snow sitting on the ground. So as we hike a little bit further on, and I know that's a little hard to see, that's actually snow on the ground. And this is George coming up through the woods. There's no trail there either. So we're just kind of fighting our way through the trees, and we got pretty tired. Snow, unfortunately, doesn't just land nice and flat. It's usually like this. So we had the challenge of going up and down these little snowdrifts, and George got a little bit tired. So what did we do? We said, you know what, we're going to have to call it a day. We're going to go back. We're going to enjoy ourselves at the lake. It was all about the journey, not the destination. And they had a wonderful time. They had a wonderful time, and that's really important as hike masters that we emphasize to the people we're hiking with. It's not about the destination. I'd say there's a pretty good percentage of the time I don't actually get to the destination, but the joy is in the journey. Let me share another question with you that I've gotten some good mileage with some students about. Let's suppose I want to know if a certain mathematical object has a square root. Okay, so we can start really simple and pick a number like 25. If I ask you if 25 has a square root, I hope that you'll all say yes. Okay, but then it gets a little harder if I pick something like 18. Does 18 have a square root? Well, now you have to stop and think, I've got to rephrase that question. Where does this element have a square root? Because if I try to find an integer square root, I'm going to now have to say no. But on the other hand, if I consider the real numbers over here, now the answer is yes. And I can go on, and this is something any student can sit down and play with, and just pick different examples of things. We can take some negative numbers, that allows us to bring in the complex numbers, right? And there's nothing that says we have to think of square roots in a classical sense. We can do them in some kind of an additive structure, okay? Like the integers under addition, or integers mod 6 under addition. But you get, even just something like that, you get a fairly interesting table where the yeses and nos are sprinkled in different ways. And it leads to further exploration, because as soon as you fill out a table like that, the next question might be, if so, how many square roots does the element have? Well, we can go back and try to answer that question. And I put the numbers there, because I'm sure you're all taking notes. After that, we can say, well, what about cube roots? We can do the same thing there, right? And we can generalize this problem in 1,000 different ways, looking at 1,000 different elements over here. And it'll be something easy to explore. So after that, we can make it even more general, and we can ask about this question in any algebraic structure. If I take an element out of that algebraic structure, are there conditions, necessary and sufficient conditions, that will provide for when an element has a kth root in that algebraic structure? And this is a nice problem from the point of view that it makes sense in lots of different contexts. There are lots of different algebraic structures. So I started out with matrices under multiplication, n by n matrices. Now this doesn't form a group, but the question still makes perfectly good sense. And it turns out that this was actually a high school student at the time. Camden Jansen was at Cal State Fullerton about 8 or 9 years ago, and he worked out this rootless matrices result, which basically was a characterization in the context of n by n matrices that appeared in the proceedings of the National Conference on Undergraduate Research. Now, to be fair, this was not a totally new result. This had been known for quite a long time, but it was buried in the literature in such a way that it was almost unrecognizable in comparison with the very modern approach that Annin used here. He actually came up with the idea of working on this project by reading Mathematics Magazine. I want to encourage you, if you're looking for, if you don't know how to think up good problems to work on with your students, pick up some of those journals that have undergraduate-friendly articles in them, because there's lots of great stuff in there that you can find good problems from. So then I said, well, what about taking, say, the symmetric group and the alternating group? I'm not going to stop to define those right now, but if you're familiar with those particular group structures, you can ask the same question again in this context. So I had a couple of other students, Trenton and Chad, worked with me a few years back, and they came up with a nice paper that went in the Pi Epsilon Undergraduate Math Research Journal that characterized that particular case. And the most recent example that I've done is, I went back to something I'd worked on as a student, as an undergraduate myself, the symmetric inverse monoid. So semi-group theory is something that I've spent some time thinking about. This consists of partial one-to-one mappings from a set to itself. So it includes the symmetric group as a subgroup of this semi-group, but this is not a group because the mappings are partial. And I had 3 students that graduated just last year, one of them is here today, that worked on this particular problem, and they also came up with a characterization of when elements in the symmetric and inverse monoid have K-groups. I don't want to go into all the details of it here. That's a whole other talk, a whole other lecture. But for now, just to suffice it to say that that was a very successful thing. This came out of a program that, obviously you can tell, if I'm hiking in the summer, I'm not doing REUs so much. But I did get a grant through the Center for Undergraduate Research in Mathematics to work with these students during the academic year. And that was a very fruitful way to conduct business with these 3 students. And the grant just got refunded for the next 5 years. So if you're a new faculty member, you want to do something during the academic year that you can support your students with, I highly recommend KERM as a place to go. And there they are, these students that I worked with right there. So, by now I'm sure most of the applied mathematicians in the room are about ready to bolt for the exit, so they don't see any applications here. What is this all good for? So I get this question a lot, and I think it's important because if we want to motivate our students to pursue creative projects with us, they have to understand that it's good for something. Okay, of course, we don't really need that motivation, do we? We're just naturally curious, and it doesn't have to have an immediate application. But I like to give people examples. So where to use math in the real world, I have a very good example of that. It's called McHenry's Peak. This is the hardest mountain to climb in Rocky Mountain National Park. You ask any hike master out there, they will tell you, this is it. This is the one. And so, of course, what did I want to do? I wanted to climb it. Well, here's what it looked like on the morning of August 2nd, 2008, a day that I'll never forget. We had hiked since 2 o'clock in the morning, and the sun is just now coming up, starting to come up. And here we are hiking towards the top of that thing. You can see it gets really tough up at the top. Really tough. Actually, you don't go up this side. You go up the back side of this thing. And so when you get over the back side, it looks a little more doable, maybe. This is the back side. We're trying to get up to the top here. But that little piece right there, it may look not that tall, but from the distance that you're at, that's probably 50 to 100 feet tall. And it's just a vertical wall. So you can't go up that way either. This is why this mountain is so hard to climb, because unless you want to use ropes, you've got to find a really accurate route to the top. In my case, that consisted of going over here to the left and kind of trying to go up the snow. And actually, it's not what you think. We actually made it up just fine to the top. The scenery is great. Made it all the way to the top, no problem. And we had a great time. I called my parents, and we just had a great time up there. And we're ready to come back down. And there's my hiking buddy, and I started to say to him, did you come this way, or did you go down that way, this way, or how was it? And of course, we're both wearing our backpacks. And you can see that in some places, the terrain was so steep that we had to almost jump down from one level to the next. It was maybe like 6 to 8 feet down. And I got to a place where I needed to do that, but my backpack was too fat behind me. I needed to take it off in order to jump down 6 to 8 feet. So I took it off, and then I said, you know what, if I jump down 6 to 8 feet, I won't be able to get my pack again, because it's too high up. I'm not that tall. So I said, oh, that's all right, I'll just set it down in front of me. So guess what happened when I set it down in front of me? It rolled off a cliff. It rolled down here. I watched it. I had a great time. Kind of paralyzed there on the ledge. I then went over to the ledge and I looked down. I couldn't see a thing. And this thing had gone 2,000 feet into the abyss. Here's a little other perspective on the same mountain from a different day. You can see all these little, it's a little hard to tell, you can see all these little canyons that are there. We had hiked up from over here on the far right. That's where we needed to go back to. Well, my backpack went down in here. And I didn't know where it was. And this thing is like a 16-mile round-trip hike just to get back into that little canyon from the trailhead. So, oh, and then this is not good. This guy, now I didn't have any trouble because I didn't have a pack on anymore. I did great, but my hiking buddies over here took him about 15 minutes to get across that little bit of snow. It's very steep in that area. So we were really in bad shape. We were not where we needed to be. But luckily, actually, he was the voice of calm. I wanted to go look for the pack. And he said, no, we'll go back another day and look for it. So here's where the map comes in, right? So let's take a topographical map, which you've all seen in your multivariable calculus classes. And here's where we were trying to get back to, Stoneman's Pass. And the pack had gone somewhere over here. So I said, I think the pack was going about, I don't know what it was going, 25 miles an hour, whatever it was, off this cliff. And this thing, here you see how close these contour lines are right here. That, of course, means it's very, very steep. We made an estimate of where we thought this pack was going to be. So after that, here's the Stoneman. And there's the mountain we were climbing. 2 days later, I went back with my friend to look for this pack. This is a different friend. He's actually a graduate student in math at the University of Kansas, so very convenient to have him along. And he was helping us try to figure out where to go, and here he is. He's using an ice axe and everything. This is that. Oh, I should point out, everything was in this pack. I wanted it back bad. I had my keys, my phone, my GPS, my wallet. I didn't have my camera with me, so I took some lovely pictures. I lost everything else. I had no first aid kit, no food, no water, nothing. So it was worth it to try and recover some of this stuff. And here's what the terrain was like. I don't know if you can see that very well. These very narrow ledges that we found ourselves stuck on. And the pack had landed on one of those ledges, about where we had anticipated that the pack was going to be. So we got lucky. I found my pack. I found all my stuff. It was there. It was all fine. Okay, Sprint wasn't that bad of a phone. It still worked after going 2,000 feet off this cliff. Pretty happy about that. Math and hiking can mix, as you just saw in that example. And it can happen in less dramatic ways as well. So I thought maybe I should share another example or two. It's a little bit of a dark picture, but this is my colleague from Cal State Long Beach, Will Murray, who I don't think is here today, but he's one of my best friends. I've known him for 15 years, went to graduate school with him, the same advisor at Berkeley. And, well, here he is having some fun on the snow. He came out and visited me in 2009. And we went on this hike together, and there's Will, and there's me, and I felt sorry for these two guys in the middle. We hiked for 11 or 12 miles just yakking away about math. This is a lawyer and a college student who are stuck in the middle of this hike. But at any rate, they tolerated it pretty well. And it was, you have all kinds of time to talk about things when you're out there on the trail. So Will had a chance to share something he'd been working on with me. And I got to tell stories of some of the fun stuff I've been working on. So Will published an article just in last year's Math Magazine, a really great article on Markov chains for collaboration. And I encourage you to read that. He co-authored that with the department chair, Richard Mena at Cal State Long Beach. And it appeared last year in the Math magazine. It's a great article that I encourage you to take a look at. And I shared with him one of the projects that I've been interested in for a long time, which really is not in my area of specialization either, but I just happen to enjoy it, something called M&M sequences. And so we went up and down the trail talking about these things. And let me just briefly tell you what this M&M sequences problem is, because I could use a little help. Actually, I'm working on this with a student, and I'll share that with you in a second. So one of my colleagues, Harris Schultz, gave a talk at a math conference about 4 or 5 years ago, where he introduced this idea of an M&M sequence. Here's the definition. If you take any 3 real numbers to start with, you can inductively define the rest of the sequence as follows. You choose the nth number of the sequence, that's xn right here, in such a way that the average of the first n numbers is the same as the median of the numbers you already have. Okay, so that will be a uniquely defined number. Xn will be unique. So the sequence is uniquely defined by these first 3 terms. And so here's an example. If you start with 52 and 94 and 148, you can calculate x4, x5, x6, and so on, and just look at the sequence. Well, the thing I want you to notice about it is that over here at the far right, it has become constant. It has held steady, and it happens to be the same number we started with here. That doesn't always happen. Okay, it did happen in this case. So the conjecture is that these things are always eventually constant. And I have no idea really how to prove it at all, but there are some observations that Harris Schultz had made that I thought might help us. For one thing, these M&M sequences are preserved under linear transformations. So addition, subtraction, scalar multiplication. If you start with an M&M sequence and you do something, if you shift the numbers, you'll still have an M. So in other words, you can shift the sequence down so that the first number is 0. Okay. And then you can also apply a linear transformation in such a way that the second and third number become spaced by exactly 1 apart. And such that x is at least 1. So this is actually something that Harris had sorted out. And they proved that as long as x is at least 21.3125, the conjecture holds that the M&M sequences become stable, and that it will take exactly 73 terms of the sequence before it becomes stable. This doesn't seem like there's any rhyme or reason to that at all. So I decided to recruit somebody else who's in our audience today, Ivan Espinoza. And Ivan and I have been working on this for just a few months. And Ivan, tell you a little bit about Ivan. He came from Texas, and he's been in the community college system for 2 or 3 years. He's the first student in his family to go to college. And what I have to say about him is that I met him through a discrete math class that I happened to be substituting for last year. So when you can substitute for your colleagues, good things can happen. But I met this guy and I said, you know, if anybody wants to work with me on something, come on by my office, we'll talk. So Ivan did that, and we've been working just for a little bit of time. He's a double computer science major, but he's brand new at Cal State Fullerton as of 2011. He wrote a program to just generate gobs of examples of these M&M sequences. And they get really neat to draw, to see pictures of them. And it's just bizarre what happens with these things. The terms of the M&M, so these are the terms along here, and the values of the sequence this way. And you can see that, you maybe aren't able to read these values over here, but x's, if you choose an x value that is just a little bit bigger than 1, you can create the sequence, and the variability in it is just remarkable. Some sequences stabilize almost immediately. Some of these ones here near the top left. Others take 73 terms to stabilize, and others take thousands of terms to stabilize. So there's a huge amount of variability, and it can be just a minuscule change in the x value that causes that to happen. So I don't have any answers for it, but Ivan's in our audience, and I'm sure he'd like some help with this problem. Today, he was, just so you know, this is a very current presentation. This happened about 3 hours ago. He was presenting something, showing these pretty pictures and some of the stuff about the program that he wrote at our meeting today. So I thought it was worth putting that in. I want to leave you with 3 final thoughts about mathematics and mountaintops. The first thing is, life is way too short to be doing things that you are not passionate about. Whether you're a student or a faculty member or whatever you're doing, find things that you're passionate about because that will make you better at them. You'll do those things well and you'll live a life that is very full and filled with happiness. I have had the tremendous pleasure to be able to do this through my entire career. And if I could wish one thing for all of my students is that they would also find the same kind of passion that I have found. You know, it's estimated that 98% of the people that go hiking in Rocky Mountain National Park never go more than a mile from the nearest road. Instead, what they do is they drive around in their cars, and this is what happens. And this always annoys me. In this case, it's understandable. This huge elk is blocking the road, so of course the cars are going to stop. If that elk was over here in the forest, all those cars would still be stopped, blocking up the road, trying to take pictures of it when I'm trying to get home. And it's like the 57 freeway, but without the good excuse that there's a lot of traffic in Southern California. This is actually has an official name. It's called an elk jam. And there's nothing you can do about it. You just have to wait. But I prefer to be a part of the 2% of the people that go to the park who want to get away from the mainstream, who want to get away from the crowds and go explore and discover things on their own. And it might be something like this, you know, and we ended up in a blizzard by the time we got to the top of that mountain. Couldn't see a thing. But at least right now, we're pretty good. So, you know, these sorts of activities are the kinds of things you'll remember all your life, I think. And so I'm a little bit preaching to the crowd here because I feel like the people in this room are probably among the 2% who are doing more than just sitting in a math classroom, right? You guys are all here. But on the other hand, we have a lot of people that we can reach out to and encourage to become part of this minority of people that really do more than just sit in our classes. They go to conferences. They take the Putnam exam. They serve the math club. They present their research. They give talks. All kinds of things that our students are doing. So take mathematical hikes and encourage your colleagues and your students, as many of them as possible, to take hikes beyond the classroom walls. Because if you do that, you might just find something that you're really passionate about that you haven't found so far. And the third thing I want to say, the last thought here, is anybody with the proper motivation can achieve mathematical success, both inside and outside of the classroom. Anybody can do it if they're properly motivated. I have to go back to Jairo again. I met Jairo in 2004. There he is. He's a young kid. And I didn't really notice him that much back then. He was taking my first semester calculus course. And it was several years later when he ended up doing all that outside of the classroom work with me on the Fibonacci numbers. But he really changed a lot over those years, and I think getting outside of the classroom was a big part of that for him. This is the kind of thing that motivates me, and would motivate anybody who's a hiking enthusiast to want to get out of their cars and to explore and discover new things. And that's what I really hope that you guys will do, mathematically speaking, is to try to get away from the roads and do this sort of thing. Anybody with proper motivation can do it. So a few years ago, my parents were starting to look at some of these kinds of pictures that I was putting up. And, they weren't really hiking much back then. They had some health issues, and they just didn't, they were kind of in that 98% for quite some time. But one of the reasons why I chose to dedicate this talk to my parents is because they did the hard work, got inspired, got motivated, and one of my favorite all-time pictures of my mom is 2 years later. She had gotten herself into the kind of shape to get herself to the top of this mountain. Just to give you some perspective, you see that mountain right there on the left? That's the same mountain as that mountain. And she was standing on this mountain, and I was shooting her picture across this way. This is a 20-mile trip, and it's not easy. So it doesn't necessarily have to be something that takes years and years to get from point A to point B. For my mom, it was a couple of years. And just last year, I took my mom and dad to the top of their first 14er in Colorado, the highest point they've ever stood in their lives. They're up there with the clouds, having just an amazing time. So, you know, when you're willing to explore and discover, the view is great. You can see things that you've never seen before. That's true in the hiking world, and that's true in the math world. So with that, I think I'm going to close, and thank you so very much for having me.